Okay, we're going to be working with systems of linear inequalities. Now, um, let me take you back through. We've seen this idea before with just one inequality. How do we work with for instance, just this first one? So we saw this in an earlier lesson on how to deal with this, but now we're going to put them together as a system. And just like we saw with linear equations, what it means is that these two lines exist in the same universe, these two inequalities in the same universe, and in other words, on the very same graph. And so there's going to be a lot of parallels here, but inequalities are going to make this a little more complicated. The first thing we'd want to do is answer the question, is a particular point a solution to the system? Now, what we saw with lines is that if a line was, or a point was on both lines, it was a solution to the system, which meant it's on both lines, they must be touching at that one point. Now, with inequalities, it becomes more complicated because we have huge ranges that will get created, which we'll see in the next few slides. But the principle for finding if a point is a solution is the same. So what we're going to do, I'm going to put this point, negative 2, 4, into each of the equations, and I'm going to see if it makes a statement that's true. So I've put in negative 2, 4 here, substituted it into the first equation, which is what they're doing on the left. And after you crunch this down, you get left with 14 is greater than or equal to 10. Well, that's true. Now, we put that same point in to the equation on the bottom. We crunch it. We get negative 14 is less than 12. Both of those statements are true statements. Therefore, this point must be a solution to the system. It makes both of them true. Now, if we try 3, 1, a totally different point into both equations, the one on the left turns out to be false. So 3, 1 is not a solution to this system because it isn't true for one of the inequalities. So this is the same idea we saw with lines. The only difference is now we're looking at inequality statements instead of just equal to. So since 3, 1 is not true in both of them, it is not a solution. It has to be a solution to both. Okay, so we have seen this before. We are going to graph y is greater than or equal to 2x minus 1. And the secret is this. We're just going to graph 2x minus 1 just like it was a good old-fashioned line. We would start with a y-intercept as negative 1, go up 2 over 1, up 2 over 1. Now, with inequalities, we have to decide whether this line that we've created is going to be a filled-in line or a dashed line. And the key is if an equal sign is involved, so let's circle it up here. I have an equal sign involved. That makes this a filled-in line. I want to include the line. All right. Now, here's the last part. So if I want y to be greater than or equal to 2x minus 1, the equal told me filled-in line. Now, what this is saying is that I want the y's that are greater than the line that we just made. Well, if I look at the line that I've created, where are the y's bigger, greater, above it? Aren't these the greater values of y up here? And so, because it's an inequality, it creates a region. I'm going to shade in the entire region above the line. All right, now let's do it for the other line. Well, what's different now is it's a system. So we have two lines existing in the same graph, in the same universe. So let's do the other one. Now, I'm going to graph it as if it's y equals x plus 1. And I would do just like I would. There's my y-intercept, up 1 over 1, up 1 over 1. Now, this does not have an equal sign involved, so I'm going to give it a dash. It is a dashed line. Now, we've got to shade a region. Well, the region we want are the y's that are less than that line, and the lower values of y, so just looking at the y-axis only, the lower values of y are below the line. They're down here. Okay, well, I'm going to color that region too. Now it's nice on here because you have colors. But if I were doing this on a piece of paper, what I would do is I had shaded the top one direction, and then I would shade the below this line another direction. And what I've created here is a checkerboard. And in this case, where I can literally do the colors, this darker region right here is where they overlap. So this is the solution to the system, this overlapped region. And if you picked any value that was in this dark shaded region, it would be a solution. It would make both of the inequalities true. So we're just doing two individual inequalities, and we're going to see where they overlap each other. Okay, now this, I should have put some graph on here, some copied a graph to paste onto my slides. So we're going to do two of these, so this is not going to be very pretty. We're doing this top one, and I'm going to just treat it as if it was equals 3x plus 2. Okay, so there's 2. Now we're going up 3 over 1, up 3 over 1. Now this does not have an equal in it, so I want a dashed line. Now, I want the y's that are less than the line that I just created. Well, where are the less than y's? They're down here. So I'm going to do this because I don't have the power of that color they had. Okay, so that's the solution. This first one is below. Now let's do the other line. I'm just going to do y is negative x minus 1. Okay, so negative 1 is down here. Now my slope is negative 1, so I'm going to go down 1 over 1. Down 1 over 1. Now it's once again a line that doesn't have an equal in it, so I'm going to make this another dashed line. Now I want the y's that are greater than that line. Okay, well, greater than the line I just created are y's up at the top. So I'm going to make my lines in the other direction. And the solution, I know this isn't ideal. If you had colors, that would be best. But if you can tell what I've done here, this region where the checkerboard is created, that is the region that is the solution to the system. And any point, any ordered pair that you would select out of here would be a solution to the system. However, if it's on the line, it would not be, because those are dashed. They would not be included. But anything inside the region, that would make it true. Okay, so we're just going to have a couple more examples here of this. The only thing that's changed in the top one is it's not solved correctly. So we're going to solve that. Do they show it? They don't even show it. So what I would do to graph the top one is I'm going to solve this. Now the reason they did this is if you divide by a negative, so we need y, we don't want negative y, so I'm going to divide by a negative 1. Well, that's going to change all the signs on the other side. But it's also going to flip the inequality around the other way. So that's why they've done this one. Now I graphed that line. It doesn't have an equal, so it's a dash. Colored it in. Now we do the bottom line. Graph it so its y-intercept is 4. Everything else is the same. We wanted the y's, so it was dashed because it didn't have an equal. We want the y's less than that. Well, where are the y's less than that? They're down here. So we shade that in. Well, where did our two regions overlap? Well, in here. Okay, let's try another one. There's some strange things that can happen, and I'm not sure if our textbook's going to include them. So maybe I'll talk about those if... Oops, what am I doing? Sorry. Okay, I've solved that top one for y. So my intercept is 2. Now that's a slope of negative 1 over 1. So down 1 over 1, down 1 over 1. Now this has an equal involved, so this is going to be a filled in line. And we want the y's that are less than or equal to that line, so we want down here. Now let's do the other one. I've got negative 1. So my slope is 2/3, so up 2 over 3. So I'm obviously just approximating this. Okay, something like that. Now, it has got an equal involved, so I'm going to make that a filled in line. And I want the y's that are greater than or equal to that line. So I want y's that are up here. And I know it's much better with the colors when you can tell, but do you see that I've created an overlap region, a solution region, in there. Hold on, I'm trying to see. Well, I'm assuming we're going to have some that are going to do some of the twists here, so let's just keep going. Okay, so I'm going to do the lines y equals -1 and y equals 3x minus 2. All right, so y-intercept of -2, going up 3 over 1, up 3 over 1. So I'm doing the top one. It includes an equal, so I'm going to make a filled-in line. I want the y's greater than that line, so I'm going up here. Now, this is a unique thing. Do you remember what a line y equals -1 looks like? That means y always looks like -1. So it's going to be a horizontal line. And now there's no equal involved, so it's going to be dashed. And we want the y's less than that line, so that's going to be this way. Now, it's hard to tell but without the different colors, but the overlap region where I have both going on is in there. Okay, I'm hoping that we're going to not just keep doing the same thing over and over again. I'm hoping that we're going to get some of the exceptions that can happen. So I'm doing the top one here. Now, once again, though, I'm dividing by a -2, so that's something we don't see a lot. That's going to cause this to flip the other way. And do remember, if you just divide this -2 over, he's got to go to both of them. So that -2 is going to go to the -3 and make 3 halves because of 2 negative signs. And the -2 is going to go to the 12 and make -6. All right, I'm going to graph this as if it was an equal to. I've got -6 there. Up 3, 1, 2, 3 over 2. Up 3 over 2. Now, it's an equal, so it's getting a filled-in line. All right, and we want the y's that are less than this line, so we're going down here. Remember, I flipped the inequality sign when I divided by that negative. Now, let's do the bottom one. So, yeah, this is what I wanted. Okay, so we're starting at 1. We're going up 3 over 2. Up 3 over 2. Now, it is a filled-in line. And we want the y's greater than that line, so up here. Now, this is a very similar thing to what we saw when we did just systems of lines. What you see here is these don't appear. Now, my graph, it's hard to make this graphing look good, but these will not ever hit. And the reason I know they'll never hit is because they have the same slope. Both the lines have slopes of 3 over 2, so these lines are parallel. They'll never touch each other. So if I want the region below this line and above that line, they're never going to hit. So this region has no solution. There's never going to be an overlap because of the parallel lines. Now let's see. Okay, I'm hoping there's some other complicated things that can happen here. I hope we see it on this one. So I'm going to do the line y equals 3x plus 1. Okay, there's 1. That's my intercept. Going up 3 over 1. Up 3 over 1. All right, it's a filled-in line because it involves an equal sign. And we want y's above the line. Now let's do this one. So I just sent that to the other side. So I've got -4, so right here. I'm going up 3 over 1. Up 3 over 1. Okay, so this is a filled-in line. And they wanted the y's. Oh, yeah, this is good. Make sure I didn't mess it up. Yeah, this is good. This is one of the things I wanted. Now, they want to be above this line. Well, I'm going to draw these this way. Now, here's an interesting thing that's happening. Do you see the overlap region is over here? It actually turned out to be just the same region of the first line. The answer to the first line was the answer to the whole thing. Just because of the fact they were parallel lines, we wanted to be above both of them. Where does that overlap? It happened to overlap over that top line. Okay, so you can see lots of oddities like this. Sometimes they won't touch at all, or sometimes you'll get something like this where they're overlapping in a unique way. Okay, that's, I think, everything you're going to need to get through this. And so the idea is that you have these two lines in the same system, and we just want to see where they overlap.